This is video 2 for gravity. Right. In the previous one, we derived an expression for how to calculate a gravitational field. Capital G, mass of the planet, divided by the radius of the planet squared. Now, the gravitational field caused by a spherical object, such as a planet, is radial. So that means it always points towards the center of the object. And it's outside of the object. It varies as the inverse square of the radial distance from the center of the object. So, what that means then is, if we got it like a planet, these field lines are radial. So notice as you get farther away, the spacing between the lines gets wider. So that means then that the gravitational field strength would look like this. And I can turn it into a vector by multiplying by the unit vector r hat. So it obeys an inverse square law. If I were to kind of make a plot of gravitational field strength versus how far away I am from a planet, it would look something like this. What's kind of nice is that we will only be considering spherically symmetrical objects. We're not going to get into anything exotic in AP Physics. So that's kind of nice. All right, mass. Again, we have two types of mass. In a previous unit, we talked about inertial mass, where inertial mass is some sort of property of the object that kind of affects its acceleration. Gravitational mass is a property of the object, or property of a system, that determines the strength of a gravitational interaction. So, the way we find gravitational mass is we take the force due to gravity and we multiply it by the gravitational field strength. So that's how we can find gravitational mass. Now, near the Earth's surface, all objects, if we neglect air resistance, will fall at the same acceleration, regardless of their inertial mass. So let's see if we can figure out why. So again, G equals so that was a mass, or the math that we worked out earlier. So objects and systems then have properties of both inertial mass and gravitational mass. All experimental evidence has shown the two to be the same, that inertial mass is the same as gravitational mass. So to prove that, let's say we have an object. There's no air, so there's only one force acting on it, a force due to gravity. So if I were to study the forces along the y-axis, I would just get a force due to gravity. I'll say that for now, time being, down is positive. So that means the net force equals mass times acceleration. This right here is your inertial mass. All right, well, the force due to gravity, Fg, is mg. Now, this mass right here is your gravitational mass. And again, all experimental evidence says that these two are the same. So that all objects will have the same acceleration of 9.8. Again, that's only near the Earth's surface. All right. Now that we've started talking a little bit about mass, I want to mention center of mass. So let's say I have a system of objects, like a solar system. They will collectively have a center of mass. The velocity of the center of mass of a system cannot be changed by an interaction within the system. So if I have a solar system zipping through space, going around the center of a galaxy, if there's comets inside that solar system, if planets collide, if one planet falls into its sun, that would not affect the velocity of that solar system as it travels around the center of the galaxy. So the center of mass of a system, it depends on the masses and the position of the objects within the system. So if we have an isolated system, the velocity of the center of mass will not change. So before we look at some specific examples, center of mass really, it's the place where we could consider all of the mass of an object to be. So I'll use Cm for center of mass. So let's do a quick little calculation here. Let's say I have two objects, like a sun and a planet. What I would do is I would pick some sort of reference. So I'm going to choose this right here. And I would say this distance from here to the sun is x1. The position from here to the planet is x2. And then I would have a center of mass somewhere between the sun and the planet. And that would give me my xcm, the position of my center of mass. The way we calculate that between 2 points would be m1 x1. So this would be like mass of the sun x1 plus mass of the earth x2 divided by mass of the sun plus mass of the earth. Now, when we have orbit, and that's something we're going to talk about later, they orbit around the center of mass. As it just so happens, for our solar system, the center of mass is actually inside the sun. Not quite the center of the sun, but somewhere in the center of the sun. So when the Earth goes around the sun kind of wobbles a little bit. So as the Earth goes around, it just kind of wobbles. But it is possible for the center mass to be inside the sun. It's also possible for the center mass to be outside. So let's say I have two stars orbiting around each other. They would both move around the center of mass. Okay, so let's look at some common objects. If I have a uniform beam, that means its density stays the same, everything else. The center of mass will be located at the exact center, so half the length. So that's to be expected. What that means then is if we were to take a beam and draw a force diagram, its weight would originate at the center of mass. That's where we would start the vector. All right, something more exotic, a torus. Its center of mass is the exact center of it. Think about that for a second. Its center of mass is at a location where there's no stuff. We consider all of that mass to be in a place where there is no stuff. And that's really cool to think about. A boomerang. Well, a boomerang center of mass is actually right about here. That's why when you throw a boomerang, it has such a distinctive motion, very distinctive motion, because it's rotating around the center of mass. And again, we consider all of its mass to be at a place where there's no stuff. If I have a collection of points like stars or planets, I could find the center of mass. It'd be very similar to the equation above, but the equation I showed you earlier only applies to two object systems. When you have more than two, it becomes a little more difficult. Now, you may have noticed when you see someone using a beam to walk a tightrope, they use a very, very long beam that droops down. You see, see if I draw this here. So here we have our tightrope walker carrying a very long beam that kind of droops down. What they're trying to do is they're trying to move their center of mass below the wire. That makes it very, very stable. You see, if your center of mass is above like a pivot point, let's say like a ball resting on a like a triangle, it's very unstable because the center of mass is above the pivot point. It's just too easy to fall off. But let's see, here's our pivot point. If you move the center of mass below the pivot point, the system becomes very stable. So the reason why tightrope walkers use that pole is because they're lowering their center of mass to below their feet or below the pivot point so that they can become more stable, and it makes it easier to walk along that tightrope. All right, this concludes our gravity unit.